Well, good evening, ladies and gentlemen. I'm John Pethiker, the Physical Secretary and Vice President of the Royal Society, and it's my great pleasure to welcome you here to the 2014 Bakerian Lecture. Well, the Bakerian Lecture is the premier lecture in the physical sciences and is delivered annually at the Royal Society in London. The lectureship was established through a bequest by a fellow of the Society, Henry Baker, back in 1775, and the donation was for £100, which in those days was a great deal of money, given for an oration or discourse which was to be spoken or read yearly by one of the fellows of the Society on such part of natural history or experimental philosophy at such time and in such manner as the President and Council of the Society for the time shall be pleased to order and appoint. So now we know. The series of lectures, as I say, began in 1775. Well, we're in the 239th year since its inception, and this year's lecturer is Professor Lynn Gladden. Lynn Gladden is the Shell Professor of Chemical Engineering in the Department of Chemical Engineering and Biotechnology at the University of Cambridge, where she heads the Activities and Magnetic Resonance Research Centre. The group develops magnetic resonance methods to advance understanding of processes that lie at the heart of many technologies in the energy and pharmaceutical sectors in particular. She is the 2014 Bakerian Lecture, and it's my great pleasure to welcome Lynn Gladden to present her lecture.
Well, thank you very much, John, for that kind introduction, and thank the audience for attending this evening. And I hope I can, I was about to say amuse you, maybe not amuse you, but interest you for the next 40 minutes or so. And as you can see, what I'm going to talk about here is magnetic resonance, a technique that many of you will have encountered or certainly know of in the hospital environment, and that's the picture on the left. But then introduce you to some of the applications of magnetic resonance in the engineering domain, of which we'll learn more through the next 40 minutes. First of all, I thought I should start off by saying what is chemical engineering. And of course, being a creature of the modern age, I go to Wikipedia, not the Institution of Chemical Engineers. And so off I go to Wikipedia, and it's actually a pretty good definition. So the chemical engineers in the audience, I think, will approve. And chemical engineering applies the physical sciences and or the life sciences with mathematics and economics to processes that convert raw materials or chemicals into more useful or valuable forms. And the areas of technology that my group is interested in, and this is very much a group effort, lie in hydrocarbon recovery in the oil industry, chemical process technology, so the mainstream chemical industry, and in the pharmaceutical industry. Now, if you look at those three graphics, what you should think about, even though you don't understand the process technology necessarily, is that those systems are going to use and require an understanding of many different chemical species. There's often chemical reaction going on inside them. There'll be flows of fluids, gases and liquids around the many pipes. So there's lots of pipes in chemical engineering, if you're not a chemical engineer. And most of those processes will be going on at elevated or high temperature and pressure. So they're not easy to study, and almost invariably, they'll be occurring in optically opaque systems. So that represents a challenge for chemical engineers to design energy efficient and highly selective chemical processes that deliver what society needs. Now we're going to talk about magnetic resonance imaging, and certainly in the Royal Society, one doesn't talk about magnetic resonance imaging without acknowledging the great work of Sir Peter Mansfield, a fellow of this society, who developed, along with Paul Lauterbur, many of the MRI techniques that we use today. And so the phenomenon of magnetic resonance was discovered back in the 1930s, MRI really discovered in the 70s, and now, of course, in most hospitals around the world, with some tens of millions of patients being treated or studied per annum. And this is the configuration in which we would usually see an MRI system. It's what we call a horizontal bore magnet. The victim is laid out here and slid into the magnet, and it's a very noisy experience. It's like sitting next to road drilling if you've actually had your head inserted into one of these, as I have. That is not my head, but that's the sort of picture that comes out of it. And you see what happens. You are taking slice images non-invasively through the subject of interest. So even in its current form in medicine, it is more than just a camera. It's not just taking pictures of the inside of your body. It's taking maps of your blood flow. And if any of you have come across functional magnetic resonance imaging, or fMRI, those are maps, those highlighted areas are the parts of your brain that come alive, that require a blood flow to carry oxygen to those parts of the brain which are controlling hand movement in this particular study. I also did some experiments a long time ago with Unilever where they actually tried to do consumer testing using functional MRI, where they had people lying horizontally in magnets eating cornettos and seeing which part of their brain lit up. It's quite difficult to do a good control experiment for those studies. So there's one example, and now if we take this one, this is introducing you to the idea of motion and imaging. It's not looking at flow per se, but taking very rapid images at 40 millisecond time intervals, so you can see the pulsing of a heart within the human body. So MRI is a very advanced technique, but in engineering systems, we actually require developments from that. We are very interested in being able to model what we see inside these processes, and therefore we want to be able to quantify the measurements, the signal intensities that we record. We also want to get high spatial resolution, small image pixels. And in much of medical imaging, you're happy if you're getting spatial resolutions of 1.5 to 2 millimeters. And also, believe it or not, your body is mostly water, and it's certainly soft type material. And when the radio frequency pulse, which is the principle of the NMR experiment, passes through you, most of the materials in your body do not perturb the radio frequency pulse significantly. If you start putting an engineering system inside the magnet and hitting it with radio frequency, then, of course, you do get what we call magnetic susceptibility effects that you have to be very wary of when you implement the sequences. And so I'm going to look at two areas of our research over the past 15 or so years. One which follows some of the developments we've made, particularly to speed up data acquisition. I'm going to take as a case study imaging flow, although we could apply this to other areas of magnetic resonance, such as spectroscopy. And then I'm going to take a case study in industrial catalysis and look at some of the measurements we can now make at industrially relevant conditions. So here's the two geeky slides, as they'd be talked about in the press, I'm sure. So just if you don't understand anything about NMR, hopefully this leads you to understand the basic principles of what the technique is about. It's a Fourier transform spectroscopy, as an NMR spectroscopist would use it, and I'm going to take as an example the hydrogen nucleus, or we call it the proton, rather sloppily at times, I think. And let's imagine we're looking at hydrogen in water, H2O. And the hydrogen nucleus has two possible nuclear spin energy levels. And when you put your tube of water inside the magnetic field B0, so there's your big superconducting magnet. Our magnets tend to be in a vertical configuration, not a horizontal one, but actually in our laboratory we have a mixture of both. You get a splitting of those two energy levels. And then, as with any resonant phenomenon, if you apply energy of that frequency, you get transitions between those two energy levels. And in this case, it's radio frequency energy that we apply. And the useful thing about magnetic resonance is that the energy level splitting depends on the nucleus you're studying, because each nucleus in the periodic table has a different gyromagnetic ratio factor. And so our resonant frequency becomes a function of each nucleus. So we'll get different resonant frequencies for hydrogen, carbon, phosphorus, sodium, and so on, and all the others. And even more interestingly is if I look at one molecular species, all the hydrogens in methanol, for example, don't resonate at the same frequency. The actual subtle chemical changes in the environment between a CH3 group and OH group modify that splitting as well. So I get two different resonant frequencies for CH3 and OH. And as you can see, I've got 3 hydrogens in the CH3 environment, 1 hydrogen in the OH environment, and a 3-to-1 ratio in those peak intensities. So if I implement magnetic resonance properly, I've got chemical selectivity, as we call it, We can home in on one particular chemical species, and it is a quantitative measurement. And in the Fourier transform experiment, I hit the system with a pulse of radio frequency energy, cause these transitions, and then watch the return of the system to equilibrium as a signal in the time domain, which I Fourier transform into my well-known frequency spectrum. And of course, there are many thousands of researchers around the world doing very sophisticated experiments with Fourier transform NMR spectroscopy. And what I'm interested in doing is taking all the things that one can do in NMR spectroscopy and then beginning to spatially resolve them, as in an imaging experiment. So now let's take 2 tubes of water, one with a large amount of water, one with a small amount of water. And if I put those into my NMR machine, they will resonate, all the water molecules will resonate at the same frequency. Okay, I get one peak. But now if I apply an additional gradient in the magnetic field, so a spatially varying magnetic field on top of that big field, B0, so that the water in this tube sees a different total magnetic field to the water in that tube, then my resonant frequency, being a position function now of magnetic field strength, and the total magnetic field strength being a function of position, I now actually get a 1D image of those 2 tubes. So I can resolve the 2 positions of the tubes and how much water is in each of those tubes. And if I want to record a 2-dimensional spectrum, I put magnetic field gradients on in 2 dimensions. And this is really where I wanted to get to, because if we don't understand or at least recognize the principle of the measurement here, then it's hard to understand what we do to speed things up. Okay, so we think of no longer as a time domain acquisition, but we're acquiring data in Fourier space, in K space, and you can imagine, you can think of it that every time we collect a data point on this rectilinear grid, it takes time to acquire that data point. And we want to think of how we speed that up. And we would then do a 2D Fourier transform across to our image. Well, here is an image. This is, I'm not going to go through the details of this pulse sequence. This is a radio frequency pulse sequence that's used to do a magnetic resonance imaging experiment. And what it does is it excites the system once and then reads, shown by the red arrow, one line of K space. It reads all those data points along the top. Then you would let the system recover to equilibrium, excite again, and then read the next line of data points, and so on. And that is quite lengthy. That might take you minutes to do if you're going to do it in a robust quantitative way. But you get some very nice images out of it. So here is a column filled with spheres, and then water poured into that column, just as an example. And if I look at a cross-sectional image, instead of a brain now, I've got a packing of spheres, and I get my signal intensity back from the water, and no signal intensity from the glass spheres. And this is a mock-up, essentially, of a small reactor. Right, so that's an image. And then, if I want to look at how liquids or substances are moving within the reactor, I could do what I did with the heart, or I didn't take that heart experiment, but you saw with the heart experiment, where you take images rapidly, and you see how the thing is moving. But in our experiments, for the most part, what we will do is on top of the imaging experiment, which is this beast here, we add in another pair of what we call pulsed gradients. And what you're doing then is you're encoding the nuclear spin system with a phase, and then you look at the difference in phase of the spin system between that time point and that time point. And from that, you can measure the distance traveled in that time interval, big delta, from which you get a velocity. And so now for every image pixel, there was our image. For every image pixel now, you can encode that image pixel with the velocity with which the water in that pixel is moving. So this is a map of the speed with which water is flowing down a column in the Z direction. And you can see that it's a very heterogeneous, uneven distribution in the flow, which of course has implications for chemical processes. The light regions are fast flows, the darker regions are slow flows. So that's the principle of what we're doing. And I thought I'd just give you 2 examples, very different examples. This is not a chemical reactor, but I thought it would be interesting in a lecture of this nature to show you something. And in fact, 1774 isn't too far distant from whenever it was 1775. And so this is some work that we did with the Applied Maths and Theoretical Physics department in Cambridge with Ray Goldstein some years ago. And these are algal plants, very large single cell structures, and I expect there are people in the audience who know an awful lot more about these plants than I do. But the cells are large, they're about 1 millimetre in diameter, several centimetres long. And what's interesting about them, and you can see from this hand drawing over here on the right, is that people were fascinated, even all those years ago, on the apparent flow system within the individual cells, these large cells. And what the guys in applied maths wanted to understand was the hydrodynamics, what caused these hydrodynamic patterns. They wanted to model that because that would give them some insight into the metabolism of that plant system. Okay, now to do that, what they needed was high spatial resolution imaging of very slow flows. And I just want to give you an example of the slow flows and the high flows that you can, fast flows that you can measure with magnetic resonance. So here we're imaging at 16 micron resolution, so that's pretty small, and getting down to flows of 10 to 30 micrometers per second, microns per second. Okay, so let's just play a movie, and this is what you can get from optical studies, where you can see this effect called cytoplasmic streaming or rotational streaming. And this happens because the fibers that form the cell walls are arranged in a helical fashion, which cause this very interesting flow pattern. It also makes it very difficult to image or measure the flow field using optical techniques to do this. And so if you're looking at the flow up and back, so it's going along, if that's the axis of the plant cell, the flow's going around in that direction, we want to measure the flow velocity along the axis of the plant cell. And here's the example of doing just that. So 3 cross-sectional images of this axial component of the velocity in the plant cell. So the red colours are flow in the positive direction, which I've defined as this direction going to your left, and the blue colours are the quantitative measure of velocity of the system flowing in the opposite direction. Now really this is just to show to you the accuracy with which you can measure these flows and the spatial resolution. And of course, you're seeing the rotational twist of the flow as you go down through that plant. So that's slow flows, but you can also measure fast flows. And to do that, you do actually have to start modifying that basic imaging, flow imaging sequence, which I talked about earlier. And this is some work which colleagues in the group, McMantle and Andy Seederman, worked on some years ago. And now instead of one radio frequency excitation, read one line of K-space and doing the raster sequentially like that, it's one radio frequency excitation, read the whole K-space raster, and then do it again and again and again, and being able to implement that so that you can image from one excitation maybe 16 or 20 full images, full velocity images. And here are some examples of doing that, just to orient you to the idea of pipes. So here we have a long pipe in the top left-hand corner, a very long pipe with flow in the direction shown. And so we'd be looking at a transverse cut through that pipe. At slow flows, or as chemical engineers would say, low Reynolds numbers, you get a parabolic flow profile in that pipe. So zero flow at the wall, okay? And fast flow down the centre, and concentric shells of constant velocity, and we'll have a look at that later on. If we increase the flow velocity, you can see structures forming at the walls, curls and flows and vortices forming within that pipe flow. Now, understanding the hydrodynamics in pipes, particularly when you've got multiple components flowing through those pipes, is something that really does still need to be understood. And if we can image these systems more accurately, we can start to constrain and help develop the numerical simulations of these flows, which are then used in industrial practice. So each of those vector maps there, 20 milliseconds to acquire. So we've come down from minutes to milliseconds really very quickly. And those pipes there, you can read it there, 29 millimeters in diameter. So to go faster, and this is more recent work, This was very much initiated by working with somebody who those at the Royal Society will know well, Andrew Blake, who heads up Microsoft in Cambridge, who was interested in undersampling techniques. And these are now found widely throughout physical sciences and engineering, in almost all measurement techniques now. And I'll just run through the principles behind this. This is not a seminar in compressed sensing, you will be relieved to know. Right. Okay, so I'll start off with the basic principle. You all play around with JPEG files. You have them on your computer, okay? And this is somewhat related to the idea of compressed sampling. Okay, so there is a full image of a very illustrious group of scientists standing on a small hill outside their research laboratory in Cambridge, okay? And with 769 kilobytes worth of us, which is large. If we perform a mathematical transform on that image, in this case a wavelet transform, it could be any type of mathematical transform, we turn into this. High intensity pixels, shown by white, and a lot of black regions, 0 intensity. And now, if we just keep 1 in every 25 data points, the most intense, they're the ones that contain the information, okay? And then do a back transform, we reappear. We're 25 times smaller, okay, in terms of file space, image compression. But we still look pretty good. There's not been much loss of information. And what compressive sampling strategies say is, well, if I only needed 1 in 25 of those data points, so about 4.5% of the data points, why did I acquire the other 96% in the first place? Okay? So I don't want to acquire every one of the green dots on the raster anymore. That's the idea behind it. So traditionally, that's what we do. And now we can think of sampling this K-space in ever more exotic ways and then doing these compressed sensing reconstructions and actually getting some really rather nice results, images as a result of that. So that's the standard way of doing it. There's one of the schemes that we would use now. It's something called spiral sampling, and really one can play around at will, and it's jolly good fun for those engaged at the bench while I'm locked in an office. They wouldn't let me near the machine now doing this. Right, so, and that's the pulse sequence that would do that. Okay, so what is the result of being able to do things like this? So, chemical engineers, please work. This is the only time it's failed. There we go. Love bubbles. They love what they call two-phase flow, gas and liquid systems. Okay? So imagine a bubble rising up through a column of water. It's rising at a velocity of about 21 centimeters per second, which is pretty fast. And what we're able to do now using this strategy is image the liquid flow field, the 3 vector components of the flow in the x, y, and z directions of the liquid flow field around that bubble as it rises. Now, you might say, well, what use is seeing one bubble rise? Well, actually, it's quite a lot of fun for me and the people in the group seeing that bubble rise. But then you may deem that we are particularly sad. But it's a very pretty picture, and we'll talk more about the picture in a moment. But what you can do now is take this further and say, let's actually start imaging the flow field around bubbles as they coalesce and break up. And if you can actually start understanding the physics and the fluid mechanics associated with those processes, it will then impact the numerical simulation codes that practicing engineers will use to design large-scale chemical processes. So there is, apart from the fun, there is a serious side to this. Now what you should see from that is behind the bubble, there's a wake, a sort of tail of a kite behind it in blue and yellow. And if we just flip on, it takes a while to load this one, a long while to load. There we go. Individual frames there. So there's the bubble. There's the wake behind, like the tail of a kite, and that's swirling in the plane of the page. So the colour scale, that velocity, is in the direction of the screen as you're looking at it. So the blue and yellow is indicating a wake that's rotating like that in the plane of the screen. And you should just be able to see that around the bubble, you've actually got a vortex structure in the flow field around that bubble as it's moving upwards. Okay, so here is a question. John, on the way here, said he needed a gin and tonic. Most of you probably by this stage need a gin and tonic. So I gave you a gin and tonic. John didn't know I had that in the slide because if you actually stare at your gin and tonic or your beer or whatever or your sparkling mineral water, right, the bubbles do not go straight up. They wobble, right? And this is actually not well understood, why the bubble wobbles. And you can use these fine magnetic resonance experiments to explain why the bubble wobbles. And there is a wobbling bubble. It's being kept stationary by a downflow, but it will have all the characteristics of the wake behind it. And what we're going to do now is, we know how it's behaving in the axial direction. We're now going to take a transverse image and look at what's happening in the horizontal plane in the wake of the bubble. Okay? So what you can see is there's a lot of action because this feature that's moving around rapidly is associated with the wake. And what you won't be able to see nearly so well here, but hopefully you can when I blow it up there, is that you've got another set of vortices in this transverse plane moving around like this. And so you can actually map these in a time-resolved fashion. As the bubble is moving, you see the exact position of the bubble, you see the motion of the flow field around it, and you also know what's going on in the longitudinal direction as well. And you can therefore correlate the direction with which the bubble moves with the behaviour and the direction of this transverse eddy or vortex. And you can see that they're occurring at the same frequency, the changes in bubble direction, and the formation and shedding of that vortex. And you've got a direct coupling between the two. And this proves one of the theories that was in the literature, but nobody had actually ever done the experiment which allowed you to demonstrate this coupling. And that's what's particularly elegant about, or particularly nice and satisfying about this piece of work. So I wouldn't want you to go away in the belief that all we ever do is just take pictures of flows in pipes. We actually do a lot of fundamental work related to fluids as well. And then I talked about undersampling. Well, here's just a quick example of some recent work where we've got 4% sampling, 4% of those raster points being sampled. Here were the images that we had earlier on with precise flow, the parabolic flow, and the swirling flow, the non-steady state flow there. And now we can take a full 3D image of one of those vector components of the flow. And all I'm doing here is just showing the surface of a constant velocity. So here you can see, we said earlier that there'd be a cylindrical surface of constant velocity, and here is the constant velocity surface of 0.75 centimetres per second. Here we're mapping the 20 centimetres per second isosurface, as we've called it, and you can see these structures forming at the wall and moving along the pipe. And there's a lot more science to be done with that. So the next stage in development here is to say, if I want to go any faster, I'm probably beginning to reach the limit at that point. However, there are many problems in which you could say, from an applications point of view, did I ever need an image? Maybe I just want to know the dimension of something that is in my flow or within my reactor. Okay? So there is a bubbly flow, and it is not possible at the moment with any technique, including MRI, to be able to take an image fast enough that you don't get some blurring of the information if you take a cross-sectional image. But actually, an engineer wants to know often what the bubble size distribution is, because that determines the interfacial surface area between the gas and the liquid, and that's important in many chemical processes. So we abandon the concept of acquiring on a grid, and instead we simply work in the time domain or the case-based domain. And this is probably too difficult a concept to understand as we go along, but hopefully you get the basic idea, and you'll certainly see the result of it, is that here we would say this is what the profile of a bubble of size 4 millimeters looks like in the x direction. And if we Fourier transform that, that would be the case-space signal which we would acquire in an ideal world if the bubbles were that size. If the bubbles were 16 millimeters, that would be the case-space response that we would acquire in one dimension. So therefore, we can acquire just a few data points and do a statistical test, okay, according to Bayes' theorem, and say which of these two distributions do our points belong to statistically. Okay? but we never ever acquire an image in this process. So here's an example, 2 different bubble sizes. Here you can obviously take the image, measure off the bubbles sizes, and we can compare the optical method with the magnetic resonance method, and they match, mercifully. But come up to here, you're not going to be measuring those bubble sizes off with a ruler from a picture, but the magnetic resonance experiment works perfectly well. So a really neat measurement now, which we hope to implement on low field technology to be able to measure bubble size distributions during pipe flows. Right, so the last section of what I was going to talk about adds in some of the chemistry. Okay, so industrial catalysis, it affects all of us every day. 90% of our chemical processes use a catalyst. And as I've said there, the chemical industry generates more than £50 billion per annum in the UK. Now, the chemical industry has been around an awful long time, and it's been running chemical processes safely, I would add. But our understanding from the point of view of the fundamental physics and chemistry has certainly lagged behind our implementation. I have to be very careful because I've got Johnson Matthey and Shell sitting there, you see. So, this amuses me. So Octane Levenspiel is a very respected chemical engineer in the US. And on the front of his textbook, he represents reaction engineering and industrial catalysis as witches over a witch's brew. And that is because whilst John Myrig Thomas will do beautiful single-site catalysis with his zeolites, John Davidson, sitting behind him, has to turn that into processes, and that's when it becomes the witch's brew. Okay, and I'll give you some feel for the complexity of chemical reaction engineering now. So this is another piece of chemical reaction engineering tuition for you. I'm making real chemical engineers of you this evening. So the challenge here is the length scales and time scales of the processes that you look at. So there is just an arbitrary reactor that we've shown you here. Dimensions often up to meters. You can have them small, but often they can get up to meters scale. And the catalyst that sits inside the reactor could be there for hours, days, so on and so forth. So very long time scales. Those reactors are packed with catalyst pellets, which have dimensions of millimeters to centimeters. If you look inside one of those pellets, they have a porous structure, like a sponge. The dimensions of the channels there would be nanometers, microns. In some cases, they could be angstroms. And the timescales for moving molecules within those structures are seconds to minutes. And then, inside those channels, you will have active sites for catalysis. So this is a picture of platinum on a titania support. The little crystallites of platinum are shown by the light regions there. And those features could be angstrom to nanometer scale, and the chemical conversions happening at a lot less than second time scale. And what the chemist and the chemical engineer has to put together are all those events happening on different time scales and length scales and optimize that. And of course, that's what we want to be able to do. So I give you an example here of a process which is very much flavour of the month at the moment. There's a lot of gas in the world. Gas to liquid processing. Okay, it looks simple. You take CO, you add H2 to it, and you get alkanes and water. So that's fuel, basically. New plants going up around the world. I just take as an example here the huge, just to give you a feeling for the scale of these things that people are designing. So a fantastic new plant over in Qatar, the Shell Pearl GTL process. Now these data don't correspond to the systems that are operating in Qatar, but typically this reaction would be occurring at about 200 to 240 degrees C, up to 45 bar in pressure, so 45 atmospheres. And using, let's say, cobalt alumina catalysts. And what you're doing here is building small molecules up into almost bespoke fuels. That's the idea behind GTL, instead of cracking crude down to smaller molecules which make up your fuels. Okay, and there's a sort of flow sheet, a very crude flow sheet of a GTL process. And there's where the action is. Okay, CO plus H2 going through to liquid hydrocarbons, trivial. A plus B goes to C plus D. It's in all your lecture notes, okay? The only problem is A plus B going to C plus D isn't the way it works. and there's just a subset of all the component reactions which are thought to happen. And that doesn't account for all the side reactions that you don't want. Okay? So what I'm trying to convey to you here is the complexity of what one is trying to do. Many questions arise, such as, are the species inside those catalyst pores gas or liquid? What can we do to engineer the material science to create the activity that we want in the catalyst and the selectivity? So if the catalyst produces products C, D, and E, how can we optimize the catalyst and the reactor to preferentially produce C? So that's really what we are trying to do. And to do that, we need to start making measurements of how these systems operate under relevant conditions. So I want to give you two examples of this. So here is our reactor now. There's our magnet. This is the fixed bed reactor. So that just means a cylindrical column with the catalyst packed in it and fixed. It's not moving. Okay, that's all we mean by a fixed bed reactor. So that's where the catalyst pellets sit. Okay. And there's a schematic of it. And we're going with this system now. We can put it inside the magnet and take our measurements up to 350 degrees and 30 bar. So verily a little bomb sitting inside our magnetic resonance instrument. Okay. Just a quick schematic. There's our fixed bed, our catalyst pellet sitting inside the bed. There's a cut through it. We're going to answer the question, is it gas, is it liquid now? And what information can we get out? So just one component we're looking at now to make things simple. So we can see high signal from the liquid between the pellets, and then we get some signal intensity from the liquid inside the pellets. Okay, that's just to orient you to the images. And then here we've sat at a temperature of 188 degrees C, and we're ramping the temperature, the pressure, up or down between these limits of atmosphere and 11.54 bar. So up at high pressure, when we're on the liquid side of this liquid vapor curve, so there's the line of the phase diagram, we're fully liquid filled everywhere. Drop down pressure to the vapor side, the liquid disappears between the particles, but still exists inside the particles, and indeed, that liquid will exist quite a long way down in pressure. Okay? But we can actually measure exactly how much liquid is in there at any point in that pressure temperature space, and we can quantify it. So we know exactly how much liquid is within the pore space of those particles. And we can zoom in, so there's a technique called zoom, NMR, and we can zoom, and we can go into individual particles and look at their individual relative saturations. So a huge amount of information, and not only that, we talked about velocity imaging. We can also measure diffusion. So we've all heard of Brownian motion, how molecules move around. And of course, that's crucial to how they move around inside the pores of those catalyst particles. And what we're doing now is inside those catalyst particles, measuring the mobility of the cyclohexane molecules, okay, as a function of pressure. And what you can see here is that you've got a changing molecular mobility as a function of pressure. Has that been designed into your process? If you went to the correlations that exist in the engineering literature, it would say that liquid cyclohexane at 188 degrees C and 12 bar moved with a mobility of 1.3 times 10 to the minus 8. Well, that's pretty near to the pure liquid situation over here. And in fact, it's a good estimate given what we call the tortuosity of the particle, the interconnectedness of the pore space. But there's a lot of vapor in this system, and the vapor diffusion coefficient that you would get out of the literature is up at 5 times 10 to the minus 7, and that's way up here, indicated by this arrow, and you're not seeing that at all inside those porous pellets. And you can start to explain this because actually the gas and the liquid molecules at the surface of the pore will be in dynamic exchange with one another. So what's happening is the liquid building up inside the pore space is slowing down the vapor molecules. But if you just designed on the basis of gas and liquid diffusion coefficients, it's not going to tell you what's really happening inside that system. Now, the final example I just want to give you is a nice one because it begins to pull all the different things together. I'm not going to go around in detail this flow sheet. You will be relieved to know. We work on this bit. This is a large European consortium that a part of the group are engaging with. And we're looking at this reaction called ethene oligomerization. That's a rather grand term for sticking ethene molecules together in a long line, like that. So there's our ethene molecule, okay? And we add another one to it, we keep the double bond, and then we get this alkyl chain developing. So a straight chain molecules forming with one double bond at the end. So that's ethene oligomerization. And it does produce some bespoke fuels, but also it's the building blocks for polymers, detergents, and lubricants. Okay, so here's our schematic. Now we have to thank Dr. Mantle for this animation. This is a good one. It's to show you the principle of spatially resolved spectroscopy inside this reactor. So here we go. There's two ethene molecules. The gin and tonic is coming. It's fine, okay? There we go. They're never going to meet. They don't react. But we can take a spectrum at this point in the reactor, local to that point in the reactor, and we just get a chemical spectrum out, which is typical of hydrogens interacting with that double bond. Okay, so it tells us we've just got ethene there. Let's set another two off. Here they come. They react. They'll start forming the alkyl chain, which I've colour-coded blue. The hydrogens there are not interacting with the double bond, so they'll resonate at a different frequency. And here it goes. And so you can monitor the extent of polymerization or oligomerization of this reaction. And in spatially resolved spectroscopy, as we implement it, you can get, in our case, 96 spatially resolved images all the way down that reactor. In principle, you can do it in 2 and 3 dimensions as well. But you'll be getting these back on the timescales of minutes covering the entire length of the reactor. So here is an example, and this we've only just started acquiring these data now. The signal intensity you're getting in the reactor is the lighter shades mean higher signal intensity. So you're getting higher signal intensity as you go down towards the bottom of the reactor. You're forming liquid products. They're associated with higher signal intensity. And at time equals 6 minutes, we've just shown you 3 of the 96 spectra. And you see what you expect. You see the growth of that blue chain, the alkyl chain, as the system polymerizes as we go down the reactor. And of course, you're taking these data quickly enough, and hopefully we'll be able to take them even more quickly as we implement some of those flow techniques across to this system. And you can get all this as a function of time as well. And with that information, you can start pulling out data such as the weight fraction of your products as a function of carbon chain length. So in the early stage, or startup as we would call it, you see a very broad product distribution. And this is seen in practice. And then over a period of an hour, it settles down to producing quite a well-defined range of carbon numbers, up to about, let's say, 10 to 20, predominantly up to about 10 carbons in a chain, and no longer. Okay? So I should say, just remind us here, that this is all happening at 110 degrees C and 28.6 bar. So quite decent elevated temperature and pressure. And of course, we can add in diffusion measurements. We can track the mobility of our ethene gas at the top and the diffusivity of the mobility of our liquid phase products throughout the reactor. So an awful lot of data to start understanding this chemical process. And then the last slide, we started off with the image on the right, on the flyer for this lecture. Let's just focus ourselves on the image on the left for the moment. So that ethene experiment was what we call a single phase flow. Ethene gas was just flowing through the system. This is not a flow field from that reactor. It's a rather old image, but it's a very beautiful image which started us off on this track. So the catalyst particles are here in black. The colour bar is showing us the liquid flow velocity down the bed at each spatial position. And I showed a small version of that earlier on. And this is just to remind you, if we look at that pellet, that catalyst particle, it's surrounded by very slow flow. If we look at that one, it's got some fast flow there. And that will influence the way reactants can get into the catalyst particle and are removed from it. So all the beautiful work that the catalyst chemist does in producing the perfect, highly selective catalyst, if it's not operated in the reactor environment, such that all particles are seeing the same boundary conditions on them, clearly you stand a chance of losing the high selectivity which you designed at the bench. Okay? And also the catalyst chemist has to produce materials which can actually scale up and are functional in a large process environment. Now, just to finish with a movie, it seemed good to finish with a movie, so we've got a movie. Two-phase gas and liquid flow, many processes will be feeding in gas and liquid, so the black regions are our catalyst pellets again. This isn't a velocity map. Where you see blue, it's gas. Where you see yellow, it's liquid. And you can see again this idea that not every particle is seeing the same environment. Some are predominantly surrounded by liquid, like that one, some by gas. And if you move away from steady state operation, and that simply means a constant gas and liquid flow rate through the bed, and of course anyone in their sane mind, if they're operating a huge process vessel, is going to want to operate at steady state. But certainly with some smaller processes now, there is interest in actually fluctuating the feed rates into these reactors and actually getting some understanding then of how the gas and liquid contacting of the catalyst changes in terms of the way you implement those fluctuations in feed rate are of some interest, because you can see that you can improve the activity and the selectivity of your process. So if I just play that movie, and what we're doing here is we're keeping the gas flow rate constant and then having a low liquid flow rate for 4 seconds, increasing it for 4 seconds and then down again. And you can see there'd be a quick burst here, bang, it suddenly becomes yellow, that image. That's where we've suddenly ramped up the liquid flow velocity. And so one can actually see how the different protocols for changing the feed rate into those reactors is actually going to change the way the catalyst sees its environment. And of course, you could change the shape of the catalyst particle to benefit from those fluctuating gas and liquid flow rates within it. So, the summary. Hopefully what I've shown you, very much based around reaction engineering, is that magnetic resonance imaging has advanced to a state now where we can look at chemical processes and hydrodynamic processes to look at problems of real relevance in the chemical industry in the areas of oil recovery, gas recovery, chemicals, pharmaceuticals, and also the food industry, of course. We've looked at the transition from medicine into chemical engineering, and alongside these developments, particularly because we can now take data much faster, we can signal average much more with these undersampling methods and other techniques being developed in other laboratories, the idea that we have to work with a large superconducting magnet begins to move away. For research purposes, almost invariably, we will use large superconducting magnets, but it does become possible now to begin to do some magnetic resonance experiments with systems that would sit easily on this bench, such as that one here, which analyses flow through rock cores in the hydrocarbon recovery sector. So with that thought, I will thank you for your attention and thank the people who have worked with me, and of course this is not all the people who have worked with me over the years. There's a picture of the group taken at a certain point in time. There's my serious partners in crime, Andy Seederman and Mick Mantle, for which this really would not have been possible without them. Paul Alexander, my other half, played a very important role in all this, because when we were graduate students, he's in astrophysics, and while I was bumbling around not fully understanding Fourier transforms, he pointed out that he was an expert in Fourier transforms and then rewrote all the astrophysics software that he was writing so that we could actually apply that into magnetic resonance. And actually, I say that in a rather jokey fashion, but it was hugely important, because at that point, all you could ever do with this software that was on a commercial spectrometer was take pictures. You couldn't extract numbers, and you couldn't analyse those numbers rigorously. And that's what we were able to do because of Paul's input. And obviously, a huge amount of work from the others that I've listed off here, in particular, Alex Taylor and Dan Holland, with a lot of the two-phase flow work that I showed. And none of this would have been possible without the research councils and many industrial sponsors over the years. So thank you very much for your attention.
Thank you, Lynn. I think we're going to take some questions from the audience.
Easy ones.
Easy questions are required. So if there are microphone handlers around them, so if you wish to ask a question, please put your hand up and the people will bring a microphone to you. So some questions. Is that the hand I see down there? No?
I should have planted some easy ones.
Thank you.
I don't know if this is turned on, isn't it?
Yeah, you can stand up if you wish.
Okay, I'll speak a bit louder. I think that was an incredibly fascinating lecture because it seems to me it's bringing in applications of pure chemistry and with chemical engineering and reactions and catalysts, and also on the other side, the physics of gas flow. Now, two things flashed through my mind as you were lecturing, and one is, are there any applications that you could use this process for regarding the exhaust gases coming out in gas emission from cars? I mean, particularly with diesel engines, there's been a lot in the press about particles formed, etc.
Yes, and there's Johnson Matthey sitting there. We haven't looked, we've certainly looked at autocatalysts, but not yet with those sort of real process fluids flowing within them. In principle, there is no reason why you can't do that. And of course, one of the, you could say often with techniques like this, well, why aren't you using the fast laser techniques to look at what's happening? And of course, the reason you can't in many of these systems is where you've got a particle-laden flow, you will get scattering off all the particle interfaces. And so the potentially much faster optical laser-based techniques won't work on these systems. But in principle, you're absolutely right. The MRI should be able to do this. And it requires some, well, it certainly will require some further technique development. When you start looking at gases, which we can do now, and we can get velocity fields in gases. Different gases have different what we call nuclear spin relaxation time, so there's some challenges there. Most of the flow fields I showed you were for liquids. And of course, when you go to gases, the nuclear spin density goes down by 3 orders of magnitude. And so you're fighting signal to noise again. And then all these undersampling techniques that I was talking about, you can either say, I take the data much faster, or you could say, I'm prepared to acquire data for a longer period, but I can do a lot more signal averaging in that time, which I think then does very much open up the opportunities to look at gas flows.
Okay.
Thanks very much. Yeah.
Okay. Is there another question in the middle there? Forward.
Thank you. I'm curious about whether the limitations of the technology would allow you to image radon 222 in norm sludge from the oil extraction industry.
I don't know what the nuclear spin characteristics of that nucleus are. It is NMR active, is it?
I don't know. I was
I mean, as long as, I don't think I fancy it in my NMR machine, but I mean, more seriously, as long as there is a non-zero nuclear spin quantum number associated with radon 220, then you should be able to get a signal off of it. And of course, then the next questions would be, what are these things which I didn't actually talk about, I took that bit out the talk, these relaxation time characteristics of the spin system, and what concentration levels you are looking at. But it's one of those things in which people will often come up to us and say, do you think you could look at this? And actually it's pretty easy to put the system in the spectrometer and tell them whether we would never be able to look at it because of the intrinsic spin properties, or whether it's something that we can develop techniques to look at. And indeed, that's very much what's happened over the years, that we've worked very closely with industrial partners, looked at the problems that they are interested in, seeing which ones we cannot address at the moment, but we think we could develop interesting magnetic resonance techniques so that we could look at those problems for them. And indeed, in some cases now, well, in one case, I must not exaggerate, But one of the interesting things here on looking at difficult systems is that I said, and I really should not be quoted on it, but this has probably gone out on YouTube or something horrible, that life is easy for medical MRI because everything's soft and floppy, yeah, and our systems are much more challenging to image because of the different magnetic susceptibility responses of the different materials in an engineering system. And of course, it does mean that some of the techniques we develop now are actually good at looking at parts of the body which are traditionally quite difficult to look at around joints or through eye sockets. And so there is that really nice interface now, I realise this is nothing to do with radon, where we could start transferring techniques back into other areas.
Yeah, very comprehensive. Thank you very much. Other questions? There's one.
I was thinking, is it not a problem that most reactors are made of ferrous metals if you have a large magnetic field?
Yes, it is. So that reactor here that we just looked at, you have to find materials of construction which avoid that problem. And so the reactor that we're looking at, let's go, oh dearie me, the famous video. That's made of silicon nitride. So, of course, it doesn't matter what the reactor is made of as long as it can withstand that temperature and pressure. And so members of the group spent a long time working with a company in the Netherlands called Zeton, who develop a lot of pilot plant for industry. Designing a reactor, of course, it's got to be leak tight, it's got to have very strong, good seals on it, and that will operate at these pressures and temperatures. And so 350 degrees 30 bar is the sort of combination of maximum temperature and pressure that we found a material of construction for. We could find materials that go up to higher pressures but lower temperatures, and vice versa. But this system that we have here, it can get up to low temperature Fischer-Tropsch conversions and many catalytic conversions of industrial interest. And as I say, if we relent on the need for high pressure or high temperature, the materials are already there to do that. But it is only ferromagnetic materials, so in principle, and we have done this, very high purity stainless steel you could have in there.
Okay, well, I think at this stage, it's for me to thank you, Lynn, for the lecture. And I should say just a few things here. I mean, it's a long-standing technique, magnetic resonance, everyone knows that, but the incredible range of applications, of course, has been extraordinary. But you've achieved three things in this talk, which are quite remarkable. First of all, demonstrating how something's very practical, very useful, applicable to real-world, economically significant problems. That's one part you expect from good science. Another part, of course, is addressing long-standing, classical, tricky, fundamental problems, such as the physics of turbulence, which you've also shown us. But perhaps equally important is it's got to be fun and entertaining. And you've shown us also that applies to bubbles. So when you all leave after the lecture today, as you look into a glass of beer or Guinness or whatever it is you're about to drink, you can contemplate the fact that actually the basic science and the utility of that is also there present. So and it's my pleasure to present you, I think, formally with the various items. Just go with the presentation for the lecture. And I think on that note, we should thank Lynn very greatly for her wonderful lecture, the Bakerian lecture.